I'm going to talk about something almost impossible to do. It started when we started to work with biomedical people in the medical school in Birmingham, and they had a problem that they had time series, but the time series was of length 6 or 7, irregularly sampled, different time lengths, almost nothing. So how do you deal with situations where you have a dynamical system where the time series is irregularly sampled, it's extremely sparse, you would still like to learn something? Of course, the answer is, well, you need to have additional knowledge because otherwise it's not possible. So this is a story that I would like to tell today, and it's going to be some ideas thrown at you, right? So I'm not going to concentrate too much on results, but on the ideas. This is a work with lots of collaborators. I'll just list some of them here. And let's just skip this, and let's go directly here. So this is a time series that was generated by 3 NARMA systems. This is nonlinear ARMA systems of different orders. So it's order 10, it's here. Then it's order 20 and order 30. And if I didn't put these vertical lines there, I don't think you would be able to spot anything, right? So this is just to illustrate that to work in the signal space, sometimes it's quite challenging, it's quite difficult. So because we have lots of data, we were able to use a dynamical system. There is a special state space model called echo-state network that we use in machine learning. But what I do here is a multidimensional scaling plot of the parameters of the dynamical system. So I had a rolling window, and the window was rolling like this. In each window, I estimated the dynamical system, and then I plot parameters of the dynamical system. And then I colored the parameters. So all this is supposed to illustrate is that if you take the right representation in terms of what is the approximation of the underlying dynamics behind this, then you get a much better separation, and with some explanatory power. Of course, our situation is quite different now, so this is a completely different line of work where you assume that you have quite regularly sampled time series and you have lots of samples. Because I would like today to talk about situations where this is exactly not true. So we don't assume that all time series are collected at a fixed, regular time steps. Each data item is a time series that has a different length. So what I'm going to do is that I'm going to represent each time series as a model. Okay? And then I'm going to do machine learning in the space of models instead of in the space of data. Why we are doing it? Especially for the medical science, there is a lot of knowledge about how time series is produced. So if they take your blood several times, they do mass spectra of the blood, they get concentrations of different proteins, for example, that they are interested in. They have a lot of knowledge about how these things are produced in terms of pathway models, which are a couple differential equations, but we know a lot about these things. So I would really like to view data as some hints, but I really want to do my machine learning in the space of models that actually have physical meaning, what is going on behind it. And so then the question is, what should be our model class? Well, it should be flexible enough to represent the variability of the data that I get, but it shouldn't be too flexible because then I can easily do overfitting. What I'm going to argue today is, depending on your task, my task is not perfect modeling of the time series. For example, if my task is classification of the time series, all I want is that my inferential model is capable to extract features that are differentiating between classes. So if I'm interested whether you will relapse from your cancer in a year or not, I have a complete pathway model that is a huge state space model with lots of variables, but not everything in the model is important for that classification task. So what I call this task-driven model simplification. And so this is what I'm going to argue today about. Okay, so what are our dynamical systems going to be? Because we have irregular time series, I need to have continuous time because I don't know when my measurements will be taken. So it's either ODE, ordinary differential equation, or it's going to be stochastic dynamical system, which is a much worse situation. but we can deal with that. So for that, you need to, so the differential of the Brownian motion is the difficult part that is there. Okay, so if you give me a particular time series, so my time series are going to be denoted by calligraphic Y, and note that I have a series of observation times and observation values, right? And they can be different for different time series and so on. So I decide to represent each time series as a model. So, in terms of ordinary differential equation, I can do maximum likelihood estimation. If I assume that I have independent noise at different observation times, then it's just multiplication of the likelihood functions at different times. With stochastic dynamics, it's much more difficult because I don't know the state path, right? So the dynamics is stochastic, so I have to average or integrate out all possible state paths that is there. So that's computationally difficult, but conceptually, it's not very difficult. So this is the expectation over all possible state paths. And my parameter is theta. OK. However, because I have very few observations, I can hardly believe that I can estimate one single model and say, oh, this is it. So my situation is much more difficult because I don't want to ignore uncertainty that is induced by two things. First, my model even don't have to be identifiable. And second, I have noisy observations that are very sparse. So I get uncertainty stemming from those two sources, and I want to take them into account in a consistent way. So what do I need to do? Well, the best thing to do is to say, if you give me observations, this is Y, and if you give me observation time, R is just observation noise, right? So that's assumed to be known. If you give me those two things, when you observed and what you observed, I can only produce posterior distribution over the models. I cannot give you a point estimate. That would be unfair. And so my objects on which I'm going to formulate my machine learning is posterior distributions over models. Okay? Now, this is really crazy. So what I want to do is I want to formulate my machine learning. So I just go a little bit here. And to show you that my original data was Y1 is the time series 1 with observation times, class label. Y2, time series, observation times, and so on. So I have n objects. I want to formulate my machine learning on D tilde. What is my training set now? Posterior distribution over models, label. Posterior distribution over models, label. Train your classifier. Okay? So now I think you will be fully justified to say you are crazy, right? Because we in machine learning know how to build classifier on finite dimensional vector spaces, maybe on some graphs, but not very fancy, right? Your input is a distribution not even in a finite dimensional space. It's in the distribution over model space. And I just would like to argue that it's still doable, right? So that's what this talk is about. So let's go back. Now, I really, really want to build a probabilistic classifier. So you give me your time series with observation time, observation values, and I need to give you a class. So this is what I really want to do. Of course, what I don't know is the parameter theta, and I don't know my state path, because I can have stochastic dynamics. So I need to integrate this out. So that's what I do. So this is just marginalization. So I get this probability by marginalizing that. I can rewrite this term, this joint probability, as a multiplication of those two terms. And of course, I am able to do it if I assume that there is no additional information for the classification task in the observation noise and observation times. And I say this because, of course, then you would need a different formulation. So if you have a problem where, for example, you have two types of objects that you observe, and actually there is a difference in observation times, so you can actually guess class based on observation times, then this is not going to work. So you would need to update it. So it's very important to put all your assumptions on the table and formulate the thing. So this is my first assumption. And the second assumption is the key point of learning in the space of models, learning in the model space. And that is if you give me information about the state, about the parameters of your model, and about what you observe, I can tell you that all I need to know is the model. That's all I need to know to tell you the class, because I can collapse all this information into the model. So if I have a model, for example, or a pathway model that is related to cancer, if I know the model, I can tell you whether it's cancer or not, right? So it would be the same if you observe some object, for example, quasar or something else. If you have a good model, you would know the type, or I don't know, the questions that you would like to ask about. So this is the key point. So this can be collapsed. Okay, so I can collapse everything into here. So then I have two integrals. And if I do it, oh, okay. Sorry. Okay. If I just continue, that's marginalization. That's going to be the blue thing there. But what is the blue thing? It's just the posterior distribution. It's a posterior distribution over all my models, because model parameters are theta, given the observation. So what is this? It's just the definition. Oh, I don't know what happened there. But this is just the definition of the expected value, right? So all I'm doing is you give me observation y, and I'm doing the expected value over all possible models. And each model tells me what is its opinion about the class, right? So I'm averaging over ideas about the possible class based on models. And this is the key. This is absolutely the key. So my classifier is operating on posteriors, but the way I build the classifier is that what I really, really need is this thing there, right? Because the posterior I get from the model. So my classifier really is here. And why is this important? We deliberately did it like that because if you say, I want to build my classifier on posterior distributions themselves, then I give you a counterexample. So there is something that is called distributional classification in machine learning. We have distributional kernels and so on, so you can do it. You are in a hospital and you lie in bed. I can take your blood every hour, right? And now I have a very nice time series of your mass spectra. So my posterior about what I think is your biological system model is pretty certain because I have lots of data about you. So I have very peaked posterior. If you come to hospital every day, twice a day or something, and I take your blood twice a day, then my posterior is going to be very broad. But the disease is the same. So say I have two identical people with the same disease, the same biology. So from the point of view of classification, I should treat them as indication of the same disease. However, distributional classifier would think, oh, this posterior is very peaked, this posterior is very flat, very different things. Separate them, right? So in the space of distributions, this would be very different thing. So the only way to avoid this problem is to build a classifier in here, in the space of individual models, and then impose the posteriors on top of it. So this is absolutely the key. And that's why all the other traditional machine learning methods that operate on distributions will fail, right, in this case. Because you cannot make two data items different if they have the same physical substance and you just happen to observe one more than the other. They are not different. You're just observing them differently, right? And so this is the key. Okay. So that's I was there. So if you do this, then how do I train these classifiers? Well, I have my data set, as I said. This is my transformed data set. So I have a set of posteriors over the models given class labels. Now I can pick my favorite probabilistic classifier that will be here. It can be logistic kernel regression, as we use here. It can be Gaussian process classifier, whatever. So this is the classifier that is in here. It has 3 parameters. So this is what I'm going to train on. And my classifier really is here, but this thing I can do outside. And then you can just train your classifier as normal probabilistic classifier, but instead of probabilistic classifier, that would be this thing in here, you have to plug in this. So you have to derive all the training equations and so on based on that. It can be quite challenging because this can be a pretty complex density model, but methodologically, it's doable. Okay, so that's all I wanted to say. So, for example, you do it like this. So this would be maximum likelihood estimation, but you can do Bayesian. It doesn't matter, right? Once you have this trick, okay? So let's see what is happening. So I just give you this. So this is stochastic dynamical system. This is just an illustration. It's a two-well, double-well system, and this is a potential. So the first double-well system is the blue thing in here. You see that it has two wells there. One is higher than the other, so you are expected to be more here than here. So this is actually a stationary distribution, right? So the higher, the deeper the well. Right? So there are two systems. So two classification problems. One is the blue double well. The other double well is red here. This is a bit easy because one is much more dominant to the left and the other is more dominant to the right. But then you have another set of these weaker blue and weaker red, which are actually quite similar. The difference is not very, very large. And then you have multi-well systems that are there. And why do I have this example? Because I would like to show that I can solve this problem even though by ignoring the fact that it's multi-well, because I can see that for the classification, the only important thing is whether there is one dominant well, or on which side is the dominant well. So if I can approximate this multi-well system with just the double-well system, I can do the classification task. So I want to illustrate that my model does not have to be perfect. I just need to extract from my model things that are important for your task, okay? So just let me give you an example. So these are stochastic trajectories from the double-well systems. Just examples, right? So edit observational noise and so on. So you have more observational noise in here than in here. And this is from the blue system, from the red system. Now what we did, we brutally downsampled this, right? So you have to imagine that my individual time series were like brutally downsampled observations from here, like 5 or 6 observations. It's almost impossible, right, to do the classification task if you think about it, right? How can you do it? And so let's see what happens, right? So this is a classification performance. If you use exactly the method that I said, that I described, kernel logistic regression as the base classifier, and this is classification accuracy. It's leveled classes, balanced classes, so it's okay as a measure. And because it's a kernel logistic regression, this is just a hyperparameter, right? That is kernel width. And I did it because I wanted to see whether we have stable performance or not. This is what you would really like. You don't want high sensitivity with respect to hyperparameters. And you can see, the different colors in the lines are different amounts of observational noise. I think I've written in here. So the observational noise in here is 0.04 to the left, and sigma is 0.36. And then have you random observation time subsampling, and more frequent subsampling is red, less frequent is black. But actually, you have very few samples there. And you can still see that the performance is not bad. It's actually quite good. There is no way you can do this in the traditional, way with, in the signal space. So it's actually quite nice. This is the double-well system. This was the easy task where you had one dominant well on the right and the other dominant well to the left. This is the more difficult task where there was a barely distinction between the wells. One was slightly higher than the other, but not much. So of course the performance goes down, but it's extremely stable and is not bad actually for the purpose. Everything else is the same. Note that observational noise does not really reduce the performance that much. Now this is the performance on the multi-well system, where my inferential model was double-well, just double-well, right? And Of course, you overfit here because the kernel width is very small. But if you get to the stable regime, you get performances almost the same as if the true system was double well. So this is just to illustrate that I don't need a perfect model. So my dream, in doing this is that basically this helps you to do science, because if you were able to, in a semi-automated way, describe your inferential models, you have a question about what makes a difference between different systems. If you can, in a semi-automated way, find an inferential model that actually makes the difference, then you can go and investigate, because it will point you to things that make the difference between the two classes. So it's important in medicine, it's important in other things. So this is multi-well where the peaks are almost the same, so it's almost not doable, right? So, but still the performance is not bad, like it's 90%. So we were actually shocked about the performance of this, right? And this is just to illustrate an example from medical science, right? So this is a pathway model, the way that bioengineers represent it. In each node, you would have a set of differential equations. And so this is how they represent their knowledge in systems biology, how different things are produced, and so on. Now note that they have compartments. Those are the 3 different boxes there. And the compartments are biologically meaningful blocks. Like in your case, it might be like physically meaningful blocks of things. And I have a full model, that is the red thing there. Then I have a blue model. You completely ignore the first compartment, and then you go for the second and third. And the green is the simplest thing. It's just the only model is here, right? And the task is, so this is related to women's reproductive system. I'm not going to go into details of this. I'm just to give you an idea. These are not parameters, but this is a distinction between normal and abnormal regime based on behavior of the state variable. So you really need to run the system in order to do that. So it's a quite non-trivial classification task. So this is just description of it. But what I'm really interested in is what is the degradation of classification performance when my inferential model is not the same, right? When my observation times are getting smaller and smaller and so on. So let me just show you, because you don't really need to know all these details. Let me just tell you what these graphs mean, just to convince you that actually it can make some sense. So we had 2 groups of people, group 1 and group 2. Group 1 was quite frequently measured. Group 2 wasn't very frequently measured. Then you can add additional observational noise, so we make it different. So for example, the red curve here is that the observational noise is so ridiculous that you can't just make any difference at all, right? But we wanted to see how things degrade, from time to time. So this is the performance of our classifier, given different complexities, noise levels, and observation time frequencies. And this is the performance of traditional thing that machine learners would do. It's called probability product kernel. So this is, if you wanted to use kernel machines, such as supervector machine, you use a kernel because the kernel operates on distribution, so this is what you get. And why you get that bad behavior? Exactly as I said. Because you make a difference between 2 things that should be the same, just because you have different number of observation times and so on, right? Right. So I think I can skip everything because that's not that interesting. So this is my final comment on this, is that it is not necessary for the inferential model structure to be perfect model, as long as the reduced complexity inferential model structure captures essential characteristics needed for the given classification task. So my final comment is that you can use the ideas of this methodology for unsupervised learning. So if you are interested, Marco has a poster on this. What we did was we took simulated observations from binary black hole collapses, gravitational waves, produced posterior distributions over a pretty pretty good forward model that is actually generating, capable of reproducing these things, and then ask the question, how many prototypical binary systems can I deduce? And this is, I know that so far we have very few systems, so this is like a plan for the future. But it's using the same ideas, but in an unsupervised learning context. So, thank you. Yeah.